One of the skills that my PhD advisor made sure to instill in me was something he colloquially referred to as numerology. This is a practice when you're doing computational work where you want to try to interpret your numerical results in terms of special numbers. You can't always do it, but when you can do it, it's important to be able to, because you might have stumbled upon something really interesting in the results. Let me give you an example of this. Let's suppose you run your code and you're doing some massive calculation and it spits out this number. The thing you are supposed to say as a computational researcher at that point is, this looks a lot like pi. Or you're supposed to look at this number coming out of your code and say, that looks a lot like the square root of 2 to me. Or when you see a decimal that starts with 0.707, you're supposed to recognize that as 1 over square root of 2. And we use this practice all the time to try to figure out if there was something special going on in our code. Because when you see that, it's not so much that you take it as, wow, that's 1 over the square root of 2. You go back to the drawing board and you say, why would the answer be 1 over square root of 2? Can I convince myself, can I come up with a good argument for why the answer to this particular calculation would be 1 over root 2? And 9 times out of 10, we were able to figure out why that was. And I find that that's not a skill that everybody picks up. My students in particular, I find they're not always looking for the special numbers that they've encountered in their lives. Like when they see a 3.14 at the end of an answer, like it doesn't trigger that looks like a pi. And pi is the most recognizable one probably to them. I mean, 0.707, unless you're just coming out of a very intensive trig class, you're probably not going to remember what that one is. So what I've done in this Jupyter notebook is made a code that will do some of this numerology for you. This is a project under development, so I'm going to walk you through what it does and how it works, and then I gladly welcome feedback on how this thing works or what type of special number should be included. The main thrust of it is this function called find special. You put into this a decimal value, or it could be a variable, right? Maybe you've done your long code and you've saved the output as answer. You just put in answer, right? Or put in a function, whatever, something that's just putting out a floating point. And then you put in the accuracy that you're looking for. You're saying, I want to find a special number that's close to this decimal value within this much accuracy. And so you can put in any decimal that you want. Let's suppose you wanted to put in E, which never comes up with the number. Let's go x but 1. Let's suppose you put in this number for E. Paste. It's going to tell you, hey, that looks like E. And it's using the symbols, right? It's not returning to you another number. So it's returning a string output. And this tolerance factor, this is going to basically determine how wide it's looking around for. So if I make that tolerance 10 to the minus 5 instead of 10 to the minus 6, I get 1 over 31 times E times pi cubed. Now, if I see these two options, personally, I'm going to go for E because it's simpler. The simpler one is usually better, but basically the more broad you make this tolerance, the more options it's going to spit out. So this is also, E apparently is really close to 7/5 times pi divided by the golden ratio. Major math conspiracy going on here, I'm sure. I mean, 10 to the minus 4, that's only 4 decimal places. So when you get out a list like this, you just decrease the tolerance until you get down to just 1. And if there's a whole slew of options, it's going to tell you this number probably isn't special. I probably need to change the output on that to say, or you need to make the tolerance lower. So let's go find that. Where do I have that popping out here? Probably isn't special. There we go. I can say, or you need to decrease tolerance value. There we go. You're calling this function called find special. So let's start there. So I am trying to do more modular code design rather than just put the whole thing in one long cell. So this is one of my first attempts to do this. Again, I gladly welcome feedback on how I'm doing with my modular design. So the way find special works, it reads in the number that you want to put in, and then it reads in your tolerance value. It's going to count the number of special values that it thinks it has found. So that number starts out at 0. So then we're going to loop over a list called specials. This list called specials, this is all of the special numbers that we're going to look for. It starts out, when you run this top cell, it starts out as an empty list. And then we're going to add special values to it. When you want to add a special value, you put in the numerical value, so pi, e to the 1, and then you put in text to represent how you want that special value output at the end of the code. So that's going to be Greek letter pi, regular letter e, and then down here we're going to have defining the combined specials, and this is where we're going to get those fractions and things. What this is going to do is loop over everything in the specials list and is going to start combining them. So it's going to take them and multiply them together. It's going to take them and divide by each other. I do need to refine this a little bit just to make sure they're not based off the same number. So like if I have pi in the list, but I also have pi squared in the list, I don't really want it doing pi squared over pi, right? Also, we're going to raise each of the specials to a few different powers. I've currently got that going 2 through 4.5. Just because personally, I've never found other exponents to be all that valuable, but you could adjust that list if you wanted to. If you really wanted to see if something was close to pi to the 37th power, you certainly could. You could add 37 to that list. And here it's just taking that and it's adding those specials to the list, right? So I'm using add special here to add number to the power and represent the text value to that same power value. And then down here I add in square root of 2 and the golden ratio because I like those numbers. I don't really want to raise those to a power because square root of 2 to the second power is going to be 2. Like that's not really going to be a big deal, right? We're going to take care of the fractional factors later. So that's what's in this list called specials. So the main gist of the code is that it's going to loop over all those specials and look for, does this number look like this special value? And so what we want to do is compare A with each special number, and that's what we're doing in this test special. So if I go up here to test special, what I want to find out is whether A is related to the special number, right? Because I might be looking for a number that looks like pi, or I might look for a number that looks like 2 times pi, or 3 times pi, or 2/3 of pi. And so that's where we start doing some different test cases. First thing we're going to do is multiply the two together. Because if my A is a number that has the special number in the denominator, then I want to be able to cancel that out. So if I multiply by the special number, that would cancel out any special number that's in the denominator. And then we want to check for whether this is an integer, because if I was able to cancel those out, if I had integer divided by the special number, then this would be an integer now. Is this an integer? It's pretty straightforward. It just returns whether the thing is an integer. Is the number close enough to itself rounded to 0 decimal places? And that's where the tolerance factor comes in that you're passing through. And so if that's the case, then what we need to do is add that expression onto here, right? And so what I need to do is say that this A is my integer divided by the special number. Now, what if my A was an integer times the special number? Well, that's what we're going to check here. We're going to check a quotient where we divide out the special number. So if I have 3 times pi and I now divide by pi, those pi's will cancel. I'm left with an integer like 3. And so then I check for whether the thing I now have is an integer. If that's the case, then we're going to add that number out of the special text. Now I have a special check here where if the number that it determined was in fact just 1, like my special number is pi, then we're just going to print pi. We're not going to print 1 times pi. Otherwise, we're going to take the integer that we got times the special number. Now, I might also have a fraction times a special number. I might have a rational number times the special number. So we're going to check for whether this thing is a rational. In order to find that, what we're going to do is come up here to the is this a rational field. We're going to come up to the is this a rational function, where what I want to do is find out whether this thing is a rational number. So in order to do that, we're going to bring in what's called the Mediant Method. I'm not going to review how this works because I've already made a video about a year ago about using this method to calculate the rational number, the numerator and denominator that is closest to a decimal expression. And so this is going to spit out a numerator and a denominator to give you the leftover, the remainder of this number you're testing as a rational number, the closest rational number that we can find within the tolerance specified. And what we want to do is check, okay, but is this really a rational number I'm interested in? Because if I get a rational number that's 137 out of 6,042, I'm not really interested in that rational number, right? That's just some random number that came up. So I've put in a check for whether the numerator and denominator are both less than or equal to 32, just as a way of saying I want something that looks nice on paper, right? So if you're looking for a broader range of rationals, maybe you think there's a 64 hidden in there somewhere, go ahead and change one of those to a 64. This is just an artificial check that we're putting in to just return something sensible rather than we're trying to keep it from being actual numerology, right? We're trying to be scientific about our numerology. And so what that'll do is return an expression that has your numerator divided by your denominator. And so down here, we'll ask, well, did you find me a rational? If so, then we're going to add that new expression times the special text there. So that then returns whether we have found a special number, and if we did, it returns a new expression for how we're going to print out that special number. So let's see, that was test special. That whole thing we just went over. And so if it found a special number, it's going to print the expression and increase the number of special numbers we found by 1. When we get to the end here, if we haven't found any special numbers, we're going to say no special found. Otherwise, if we found more than 3, then it's looking kind of suspect. It would be hard to tell which one of these is actually the special number. So we're going to recommend that this might not be special or that you need to decrease the tolerance value. So you've seen how this works with a few simple cases here, but I really wanted to stress test this function. I wanted to see how far I could take it. And so what I've done here is set up an integral. I want to take the integral of e to the negative x squared. So I've set up a simple left-hand sum. We're going to go from negative 100 up to 100 in steps of 0.1. I'm approximating infinity as 100 here because there's not much else happening past about 100. We multiply the whole thing by dx to get an integral. And so this integral is supposed to give me pi to the 1/2 power. It's supposed to give me square root of pi. And if I run this, lo and behold, that's exactly what I get. I get pi to the 1/2 power.